Hello, everyone. Welcome to my fourth lecture of the course on the ARC challenge and program synthesis. Today, I'm going to talk about neural and neurosymbolic search. So, here's the plan. We'll talk about doing program synthesis with LLM prompting, then doing it by when you first train the LLM and then do synthesis with it, then some neurosymbolic approaches, and finally some words on meta learning and transduction. So last time we looked at symbolic methods for program search. There's some problems with trying to find a program with with the kind of methods that we talked about last time. The first problem is that it's not really scalable compared to neural network systems. So neural networks can both deal with larger languages, so languages with more primitives, more operations, and with more complicated problems, as well as find larger programs, as we will see in a moment. Then a second problem is that when you do this kind of symbolic search, as we looked at in the previous lecture, you generally start with a domain specific language, which might in some way constrain the applicability to various problems. So if we start with domain general primitives, the program might be too long, for instance. And then we have the combinatorial or discrete nature of the search space, which means that the program space is not continuous, and our best algorithms, the most scalable ones, really only work with continuous spaces. For instance, we cannot use gradient descent or Hamiltonian Monte Carlo algorithms for searching the space of programs. So the natural alternative is to just use neural networks. But even if you decide, okay, I'm going to use a neural network to do program synthesis, the question is how. The most basic way you can try to use a neural network to produce a program is by prompting it. So in this case, of course, I'm talking about a large language model. The ARC folks have some words to say about this. So this is what they say. In this method, contestants use a traditional LLM like GPT-4 and rely on prompting techniques to solve ArcAGI tasks. This was found to perform poorly, scoring under 5%. Fine-tuning a state-of-the-art LLM with millions of synthetic ArcAGI examples scores around 10%. LLMs like Gemini or ChatGPT don't work because they are basically frozen at inference time. They're not actually learning anything. Additionally, keep in mind that submissions to Kaggle will not have access to the internet. Using a third-party cloud-hosted LLM is not possible. Of course, these claims are maybe not as true now as they were when they were produced, as we will see in the next lecture. But at least for the LLMs that were around until mid of 2024, this was very true. So LLMs, just with prompting, couldn't get high accuracy on the ARC challenge. The apparent lesson here is that program synthesis by naive prompting might work fine when there is a lot of data in the training set of the LLM. So when the LLM has already seen many examples similar to the one that it is being asked to produce, but it doesn't really work well for novel domains with little data. So there is literature on trying to do program synthesis with zero-shot prompting with LLMs. For instance, there's a really nice recent paper, Is Programming by Example Solved by LLMs? And what they do is they look at three different domains. So the domain of list, graphics, and text editing macros. So lists, you get an input list of natural numbers, and you have to transform it into a sum output list. And there's a function that encodes the relation between the input and the output. This is also the example that we will consider in the lab, in the programming lab for this module. Then they consider graphic domain, and these are logo images, where essentially you can imagine a little a pen that moves around the page and, according to certain rules, produces an image. And then you have text editing macros, where you get a text as input and you have to output a text. Here I'm showing I'm showing the prompt that they use for the list domain, and they use two, one with and one without the chain of thought. So the one without goes: implement the function solve puzzle that takes a list of integers and returns a list of integers. The function should satisfy the following assertions, and then they encode the examples that the function is supposed to fit with a sequence of assertions of identity. And then there's the chain of thought version. The first bit is the same, but then it adds: please observe the relation between input and output and think step by step. Output the function in a markdown format in the end solution, and then the LLM is supposed to generate the solution. Now, the chain of thought strategy might be more redundant now with LLMs that have been trained to produce by default reasoning or a chain of thought. But as far as I know, there isn't literature yet that compares. Um, we'll come back to that in a second, but first I want to look at another example of prompting for program synthesis. And this is a paper also from 2024, guiding enumerative program synthesis with large language models. And what they do is they have these SMT problems, so satisfiability modulo theory problems, and essentially it's analogous to the kind of examples that we have already seen. So you have the statement of a problem formulated in this formal language that you see here. And then the prompt says, you are a good synthesizer. Do you know what? And then essentially, yeah, what the LLM is supposed to do is doing: write only one Lisp-like method, define fn without any built-in methods or arrays. Then there's a bunch of requirements, so no built-in functions, never violate the SMT lib constraints above, so those are the constraints specified here. Pay attention to defined functions. Ensure the response contains one and only one function. Do not include any iterations, feedback, or int notation in the function body. Then there's something that sounds a bit funny. Write it correctly or I will lose my job and 100 grandmothers will die. Don't disappoint me. Write only one Lisp-like method, define fn, that never violates the SMT lib constraints above. So there's a kind of bit of repetition for the LLM to pick up. So this additional bit that sounds a bit funny, kind of very emphatic request, is motivated by this other paper, Large Language Models Understand and Can Be Enhanced by Emotional Stimuli. The title is pretty self-explanatory. So they are trying to improve the performance by having these emotional stimuli. So that's the basic prompting. As we will see in a second, it can work fine, but it's also easy to improve on it. Is, for instance, another strategy that that they propose in this paper. And what they do here is they get a bunch of LLM suggestions for solutions to these tasks, and then they use them to update the weights of a probabilistic context-free grammar. And then they use the updated weights to search by enumeration. Well, they have a couple of different strategies for searching, but basically it's a kind of program enumeration strategy. So what happens is the LM gets the prompt, proposes some candidate programs. Mostly they are not they are not right. when they don't work, you use the proposed solutions to update the weights of the PCFG. And the idea here is that the kind of programs that the LLM proposes, even when they are not correct solutions, they are kind of around the correct solution. And so they use the kind of operators and they use them in the kind of context that the right program also does. And so then you can use this numerator with the updated rule weight to generate more candidate programs, and then eventually you might find a solution. The problem with this approach is that the LLM cannot learn from the output of the enumerator. And so they propose this other approach where essentially the enumerator uh, proposes programs to the verifier, which then sends back some counterexamples, and the counterexamples, as well as previous solutions, are integrated into the prompt to the LLM, and then this additional information can help the LLM propose better functions. So they test these in three domains: bit vector, linear integer arithmetic, and invariance. Exactly what they are doesn't really matter for us. The main thing is the accuracy here. So they do pretty well with the LLM only, but then they kind of improve on it also substantially with these other two approaches that I sketched very briefly. And so the best approach is one that uses an LLM. Um, if you look a bit back in time, so there's this paper from 2023 called Program of Thought Prompting, Disentangling Computation from Reasoning and for Numerical Reasoning Tasks. So this idea goes kind of um, a long way back for AI standards. And in this paper, they propose that essentially when it comes to answering certain kinds of questions, it's better if the LLM, instead of generating kind of a natural language answer or chain of thought, generates code. So this kind of straightforward approach where you just prompt the LLM and then do something with the output can work fairly well. But of course, a natural way to increase performance is by training the LLM additionally for the specific purpose of program synthesis in your domain. And there's a recent paper, so the one that we've already seen earlier is Programming by Example Solved by LLM, where they do exactly this. So first they tried just the prompting, as we've seen earlier, and then they tried this other strategy where they fine-tune the LLM. And the general approach that they take works in 4 steps for the fine-tuning. So they start with a manually constructed data set, and the data set contains programs and then inputs that they feed to those programs to generate outputs. And so in these manually constructed data sets, you can make sure that you have a lot of variety and kind of a nice selection to learn from. Then they kind of increase the data set by generating new examples of programming inputs by prompting an LLM on this seed, on the manually generated seed, and asking for variations of those manually generated examples. And then, of course, you can complete the data by running the input through the program to get also corresponding output. So you get all of this together and you construct a data set, and then you fine tune the LLM on the data set that is constructed in this way. So you start with the seed that is manually constructed, and then you use an LLM to generate new examples for training based on variations of these seed examples. And so what this plot shows uh, is the performance for the 3 domains that we saw earlier: lists, strings, and graphics. And the y-axis has the percentage of problems solved in some representative set of tasks. and the search budget. So how many samples do they get from the LLMs? These two LLMs, so ours 33 billions and ours 7 billions, are the fine-tuned ones, and all the other ones are kind of baselines. And as you can see here, the fine-tuned models perform very, very well compared to the other ones. And they also show some baselines of other program synthesis methods, um, like, for instance, Dreamcoder, that we'll talk about later. So that should have given you an idea of the kind of approach, the kind of things you can do with just prompting and fine-tuning the LLMs. And then if you want to do something fancier, you can think neurosymbolic. So what does that mean? That means that you construct an architecture which combines these different approaches. In a sense, this approach that we saw here is also neurosymbolic. But let's have a look at the other options that you have in this space. So here I'm using a really nice illustration of the options from this paper. And they categorize kind of schematically the neurosymbolic architectures into a few categories. So they say neural guided search, symbolically guided deep learning, distillation, relaxation, and component discovery. So let's take them one by one. What's neural guided search? Well, neural guided search is when you have a symbolic space of programs, for instance, defined with a PCFG like we have seen, and then you guide the search through the programs using an LLM. So for instance, you have a partial program, and we in the last lecture, we've seen that one way of exploring the space is to just kind of exhaustively fill it with all the possible rules when you do top-down search. But here, instead of kind of going through all of the rules, you just let a neural network pick the most promising application, and then you use this to explore some branches of the tree of possible programs. Then you have symbolically guided approach, neurosymbolic architectures, where you have the some kind of symbolic representation of your theory that guides the neural search. And this can be useful, for instance, if you have some prior domain-specific knowledge that you think can help with the program search. Then you have distillation, and here you have you train a neural network to perform a task, and then you distill it into a symbolic representation. So at the end, in the end, you have a program that is a distilled version of a trained neural network. And then you have kind of intuitively the opposite, where you first get a program, and then you relax some parts of it into a neural network. For instance, you replace some nodes with neural networks that then you can train to get a more, for instance, a system which is, for instance, more robust to noise. And then you have component discovery, which I already mentioned in the last lecture. So that's the kind of library learning stitch style, where you have you have a kind of neural network which can generate programs, and then you can discover components which are programs that then can be reused by the neural network for further search. So here we talked about the various architectures you can have, which have kind of which are neurosymbolic in that they combine neural networks and some kind of symbolic component. But then, of course, the programs itself, which are found through these procedures, can be neurosymbolic. So they can also include some symbolic component and some neural component. And this is also a plot from this really nice paper. And so here they distinguish four kinds of neurosymbolic programs: um, additive composition, neural after symbolic, symbolic after neural, and branching composition. So how do they work? Well, additive composition, essentially you have a neural network and then you have some symbolic program, and then you just compose them additively to generate the prediction. Neural after symbolic, you have a neural component and a symbolic component, and then you feed both of them into a neural network, and then the output of this final neural network is the actual prediction. Then you have symbolic after neural, where here you have a bunch of neural networks, and then they get somehow combined through a symbolic procedure, and then the output of that symbolic procedure is the prediction. And then branching composition, where you have a conditional that, according, for instance, to some feature of the input, decides whether to predict using a symbolic expression or using a neural network. So this gives you kind of an overview, but again, I went through it very quickly, and if you want more detail, you should come back to the original source. And then I wanted to kind of go into a bit more detail on a specific example of a program synthesis system that has been very influential, namely Dreamcoder. So how does Dreamcoder work? Well, what it does is it grows new concepts. Why is growing new concepts useful? Well, if you grow concepts in a strategic way, so you make sure that you grow concepts which are useful, and then you can use them to infer shorter programs given the kind of environment of problems that you inhabit. That also means that you can adapt to your environment better if the programs that you grow depend on the tasks that you encounter in the world. Um, in order to do this, Dreamcoder uses essentially an older version of Stitch. And what it does is it learns implicit procedural knowledge. So it uses a neural network to search the space of programs. And it does so based on the data itself. So it looks at the data and then searches based on that. This is in contrast, for instance, to the symbolic approaches we looked at in the previous module, where, for instance, if you're enumerating, you're just going through the programs in a non very goal-directed way. It's not directed by the data that you are trying to learn a program for. This is hard to do. So this implicit procedural knowledge is hard to encode in symbolic terms. Intuitively, it's more of an intuition. So if you're trying to produce programs for logo graphics, for instance, and you see a graphic that has a lot of circular shapes, then you might think, oh, well, I'm probably going to need some visual primitives that are circular, maybe like a circle or in a constant curvature and so on. And these kind of associations between data and your expectations of what the program is going to look like is very hard to encode symbolically. So instead, you can train a neural network that proposes programs from observations. This is the general structure of Dreamcoder. It consists of three phases: wake, abstraction, and dreaming. So let's look at them one by one. The main questions here are: how do we grow new concepts? And how and when is the artificial neural network trained? And the solution to this is in this wake sleep program learning approach. So let's look at the phases one by one. In the wake phase, you have a bunch of tasks, which each consist of some input-output pairs that come from a single program. And then for each task, you find the best program that solves the task, in the sense that it finds a function, it finds a program that fits the input output pairs for the task. Given the current library L, what's the current library L? L is basically a set of concepts of functions that you grew and that you can use as primitives in your CFG. The search is neurally guided. So you have a recognition model which proposes the next rule to apply to a partial tree, and you can do this recursively until you get to a complete program. And importantly, the network also conditions on the data that it is trying um, to find a program for. This is a small detail, but for Dreamcoder, the network only actually sees the immediate context of the tree rather than the full partial tree. Then you have the abstraction phase. So what you get from the wake phase is proposed solutions for the tasks. And in the abstraction phase, you grow your library, L. So what you do is you have all of these solutions, one for each task, and then you find abstractions, so functions that are reused across solutions. So what you do is essentially what programmers call refactoring. You propose new routines that simplify the individual task solutions. And then finally, you have dreaming. And in the dreaming phase, you train the recognition model to predict the best programs for tasks X and the updated library. So the problem now is that you have this new library, which can have new abstractions, new concepts, new routines, and the neural network that you used in the wake phase doesn't know yet how to use these new concepts that you found. So you need to train it to use these new concepts in searching for a solution to the task. And the way that it works is you train it both on fantasies and replays, where the fantasies are essentially imagined problems, imagined tasks, and replays are tasks that you have already seen. So you recall a task that you solved in waking, and you train it on the compressed solution. So they test Dreamcoder on many domains in the original paper. For instance, list processing and text editing tasks of the kind that we have already seen earlier today. And what they do is they always start with general purpose functions. So functions that are very, very general rather than, for instance, specific text editing functions. And each round of abstraction builds on concepts from the previous leap cycles. So when you have done these three phases, you can start again from wake. And every time you have new concepts, which ideally allow you to kind of search more efficiently for solutions to tasks that were previously too difficult. And so on each cycle, you should be able to solve more and more difficult tasks. For instance, if you're doing list processing, you might first learn filter, the filter abstraction, and then you can use that to learn the concept of taking the maximum element of a list, and then use that to learn a new routine for extracting the nth largest element of a list. And then finally, you can use the abstraction that finds the nth largest element to produce an abstraction which sorts lists of numbers. So this is the performance of Dreamcoder in these two domains. compared to various other options. For instance, these models that lack the abstraction phase or the dreaming phase, and then some simple baselines. Um, Now, of course, Dreamcoder by now is a bit old, so the performance of current architectures is much better. But this was very influential, and I think a lot of ideas that came later started with this paper. You can also look at more intuitively creative domain than text editing and list processing. So they discuss this in the Dreamcoder paper. For instance, you can generate images, plans, and text. Um, Here you have logo programs again. They were introduced actually in the Dreamcoder paper for this application. And the Dreamcoder can then learn some abstractions that are parameterized by some, well, they have some parameters that allows for variations within that abstraction. And these can be used to then solve these problems, these tasks. And then they can learn higher order functions, which are kind of more abstract rather than just being a shape. They, for instance, manipulate shapes. So an abstraction here might be radial symmetry. Um, Similarly, for the domain of tower building, here you might learn an abstraction for for constructing an arc or a wall, and then higher order functions for constructing, for instance, a pyramid or a bridge. So they've also, in the original paper, used Dreamcoder to learn physical laws and mathematical identities from quantitative measurements. So what you get is measurements of physical quantities, and then you have to find the law that describes those measurements. For instance, in the domain of mechanics or electromagnetism. Um, And again, you see this pattern where you first learn simple concepts like inner product or vector sum, and then more complex concepts like the inverse square law that use the simpler concepts. And then finally, it uses these complex concepts to formulate the solution to the tasks, right? Like Newton's law of gravitation. So this is a really nice plot from the original paper where they show kind of the stats of abstractions that emerge over the iterations of these three stages that end up with rather complex solutions to the tasks. And the interesting point here is that the LLM, for instance, finds um, Coulomb's law, and in the end, it ends up being quite a small expression when compressed with the abstractions that it found. But if you take that final solution and rewrite it just in terms of the abstractions of the first generation, so the starting abstractions, then it's much, much longer. Okay, finally, I wanted to talk about meta learning and transduction. So, meta learning is a fancy name for a simple idea. So, what you have is you have a system that learns across a wide range of tasks. And in each case, it has just a few examples, and then it has to propose a solution. And what you do is yeah, so you train this network on very many of these simple novel tasks, and then the network develops an ability to learn from few examples. So you're teaching the network to learn efficiently from few examples. There's a nice overview from 2020 meta learning in neural networks survey, and it's a very rich field. People are looking into many directions. But for in our case, we are most interested in how to use it for program synthesis, and we'll look at it more in the next module, specifically for the case of the ARC challenge. And then finally, we have induction versus transduction. This is a topic that's going to come up again next time as well. So induction is essentially what we've been doing. So you have some task which consists of a set of input outputs, and then you infer a program, which for instance can be a Python program or a program in a domain-specific language that then uh, you can use to predict a new output given an input uh, that you don't know the output of. So you can kind of make a guess for what the output of the unknown program would be for the given input. So when you do this, you go through this abstraction, right? So you have some data that you know has been produced by some true underlying program, and then you have a new input data, and you produce a guess for the corresponding output, going through this abstraction of an explicit program that you found. And that's what we call induction. Although, as I've already mentioned in a previous lecture, I think a more appropriate name for this would be abduction, but induction is the term that stuck. And then you have transduction, and basically the idea with transduction is that you don't go through the abstraction. You just you have the your training kind of input-output pairs, and then you directly produce a prediction for the output given the test input without generating an explicit program. Both of these can be trained with meta-learning, and we will see that in more detail when we discuss one of the papers from the last competition, from the 2024 ARC Challenge competition. So one challenge with this approach is that you need to get kind of good training data for many tasks, for meta-learning. And then you have the problem, how do you produce artificial data? We've seen, well, they do it in Dreamcoder. We've also seen another example earlier today where you start with some seed data and then you expand it with the LLM. You don't need just new functions, tasks. Those are, well, they are not trivial to generate, but you can just produce them from the grammar. But also you need good examples to learn these abstractions from. And that's quite hard because, as you will quickly notice if you try to produce some training examples from a given program, often examples don't quite illustrate the behavior of the program. So this is not at all a trivial task to find good examples. For instance, if you have a rule that takes a list and returns the first element of the list if the returns the second element of the list is the first if the first element is equal to 1 and otherwise returns 2. Well, if you have this training set, this doesn't really demonstrate the behavior of the function. So what you're probably going to learn instead here is a function that takes a list and outputs the number 2. So I think this is basically an open problem. We're still not sure how to do it, but it's also a very interesting one. And finally, I just wanted to give some honorable mentions of things that I'm not gonna go through, but are interesting because they are not as useful for the art challenge, but are still very important if you're interested in getting into program synthesis. So there's counterexample guided program synthesis. There's version space algebras, which are also used in library learning. There's Sketch, There's Monte Carlo research, so you have all of these reinforcement learning algorithms for program synthesis. There's genetic algorithms. We've seen kind of similar things with particle methods in the last lecture, but there's a library, for instance, PySR, which does this very nicely. It has a very nice API. You have constraint-based verification. You have SAT and SMT solvers, which have been optimized to hell and are very efficient for program synthesis. Okay, that was it for this lecture, and I hope it was useful. And if you have any feedback, please send it through YouTube or through the anonymous feedback form. Um, I might also update the material at some point. So if there's anything else that you would like me to go through, let me know. And there's gonna be a lab where that goes through program synthesis with LLMs using both naive prompting, which doesn't really work well for the example in the lab, and fine tuning, both supervised fine tuning and with GRPO. So that's a kind of exciting new reinforcement learning algorithm. So go and check that out. And otherwise, I'll see you for the next and final lecture on the ARC challenge.